In this video, we're going to look at how Huckel theory can be used to predict the resonance energy in conjugated polyenes. Okay, so in this example, I've got 1,3-butadiene. There's a double bond here, double bond there, carbon atoms, 4 of them forming our pi system. So each of those carbons is going to be contributing 1 electron to our pi system. So there's a total of 4 electrons. So we're going to have 2 occupied orbitals in our pi system. So according to Huckel theory, since this rest of this molecule is planar, since pi orbitals overlap very weakly with each other, and since they're out of plane and thus non-interacting with all the other orbitals, our entire basis set for forming the orbitals of the pi system is just these pz orbitals coming out of each carbon. So we want to know the coefficients of these 4 and use that to get what their energies are in our pi system. But we're particularly interested here is how resonance plays into effect. So if I've got my skeletal structure, there's only 1 carbon between those 2, so this pi system forms a nice extended overlap, forming what we can call resonance. So how does this differ from if we just had 2 adjacent, say, ethylenes, or if these were isolated instead of if they're nice and conjugated like this? Okay, so we need to form our secular determinant matrix for these 4 carbon atoms here. So as we have 1, 2, 3, 4. So applying the rules of Huckel theory to this molecule, what we're going to have is, so H11 is going to be alpha, H22 is alpha, H33 is alpha, H44 is alpha. If I equals J for Hij, it's going to be alpha. And the other case we need to look at is if carbons are adjacent, then Hij is going to be beta. So 1 and 2 are adjacent, so that's going to be H12 and H21 will be beta. 2 and 3 are adjacent, that gives us a beta, and 3 and 4 are adjacent, that gives us a beta. So what does this look like for our determinant? So we're going to have alpha minus E, alpha minus E, alpha minus E, alpha minus E down our diagonal. All this equals 0. 1, 2 is going to be beta. 2, 1 also beta, adjacent to one another. 2, 3 and 3, 2 adjacent, so there's a beta. 3, 4 and 4, 3 adjacent, so there's a beta. Everything else is more than 2 carbons apart, so you get a 0. And that's all it takes. So now we just got to solve this determinant for the value of E. 4 values of E that we're going to get from these 4 orbitals, 4 atomic orbitals, which will combine to give us 4 molecular orbitals with 4 energy values. Okay, so what we can do is, to help these calculations along, is we can factor out beta and define X, which is defined to be alpha minus E over beta. Now, what does this help us do? So if we do things this way, what this determinant becomes, if you work through the math, is beta to the 4th, being that there are 4 rows and columns there, it's going to be beta to the 4th, is X, 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 1, 1, 1, 1, 1, 1, fill in the rest with zeros. So what I've done here is just turn this into something that's much more numerically convenient to work with in that now I just have to solve for a determinant which has really only 3 values in there. So if you expand out this determinant in terms of expanding a 4x4 determinant, not always the easiest thing to do, but in this case, because of all the zeros, if you work it through it, it ends up simplifying out to x to the 4th minus 3x squared plus 1 equals 0. Now that's the real reason why we did this. This is a much simpler characteristic polynomial than we got last time, if you remember doing it for ethylene, when it just looked like this quadrant up here. Okay, so if you solve for the roots of this polynomial, which is maybe still, yeah, it's probably still one you can do by hand. In general, you can't solve fourth order polynomials by hand very easily, so you might want to have some type of mathematical program to help assist with that endeavor. But what we get if we solve for all the zeros of this equation is x equals plus or minus, then parentheses 3 plus or minus square root of 5 over 2. So that gives us four values because there's a plus or minus inside the parentheses and a plus or minus outside the parentheses. So there's a double bifurcation there, giving us 2 times 2, giving us 4 total solutions. So if you solve for what those are numerically, you get plus or minus 0.62 and plus or minus 1.62. Okay, so if we plot this out and see what these energies are graphically, remember our alpha is kind of defining the scale of the zero of energy. So if we say, let's pick a better color, let's pick green. Okay, alpha is there. Then let's say we have 0.62, 0.62, about 40% bigger than that. It's about there. Okay, so we fill all these in. 2 occupied electrons there, 2 occupied electrons there. This is alpha plus 0.62 beta, alpha plus 1.62 beta, and the reverse of those, minus 0.62 and minus 1.62 beta. Okay, so that's the total stabilization there. If you remember from the previous video, the energy of the pi system of ethylene, if I can write that, so E pi of C2H4 is equal to, well, we had one occupied pi orbital, which was at alpha plus beta, so doubly occupied 2 alpha plus beta. So equals 2 alpha plus 2 beta. And if you look at the energy of twice of that, that would be 4 alpha plus 4 beta. So that's the energy of 2 isolated ethylene systems, and that's also the same energy we would get if we didn't have this coupling element there. So if this H23 and H32 was 0, you would just get 2 distinct non-conjugated systems there. So all the resonance energy is coming from the fact that this H23, H32, that Hamiltonian matrix element is non-zero. This is where all the resonance effects come in for this system. So if we look at twice the energy of this relative to the energy of our system in our 1,3-butadiene, which is our C4, 1, 2, 3, 4, 5, 6, yep, C4H6 equals, well, we have 2 times alpha plus 0.62, 2 times alpha plus 2 times alpha plus 0.62 beta, and 2 times alpha plus 1.62 beta. So 0.62 beta plus 2 alpha plus 1.62 beta. Carrying all the math together on that, what do I finally get? If I look down at what I wrote on my paper, it's 4.48 beta. Okay, so if we subtract this minus twice of that, that's the kind of what we're defining as our resonance energy. So E resonance equals E pi C4H6 minus 2 E pi C2H4, which if you carry through all the math there, do all the cancellations, you'll have the resonance energy of C4H6 is equal to 0.48 beta. So you notice here twice of this is 4 alpha, 4 beta. Subtract off the 4 alpha, subtract off 4 beta. So 4.48 minus 4 beta, you get 0.48 beta left. And we know from the previous video that beta empirically is around minus 75 kilojoules per mole. So that comes out to be approximately 36 kilojoules per mole. So that is the extra stabilization due to the fact that these pi systems are conjugated and they can overlap and couple through that coupling element in the matrix, give us an extra stabilization and be about 36 kilojoules per mole lower in energy than if they were a separate pi system.